morning, good afternoon, good evening, depending on where you are in the world. Um, Hello, and thank you for joining us for today's webinar. My name is Steve Cash. I'm the Director of Customer Enablement at Vitech, and I'll be your host for today. Today's topic is Precision Digital Engineering with Vitech MBSE in BigLever PLE. Today we are joined by Dr. Charles Kruger of BigLever Software and Brian Selvey of Vitech. Dr. Charles Kruger is founder and CEO of BigLever Software, which for over 20 years has helped organizations adopt and benefit from feature-based product line engineering. With more than 30 years of experience in systems and software engineering practice, he is a premier speaker, widely published author, and acknowledged thought leader in the PLE arena. He served as lead editor for the ISO IEC 26580 standard on feature-based PLE, and past co-chair for the NCOSE PLE International Working Group. Dr. Kruger received his PhD in computer science from Carnegie Mellon University, where he helped to pioneer the field of systems and software product line engineering. Brian Selvey serves as Vitech's Chief Innovation Officer, where he is responsible for managing the R&D department and the product portfolio roadmap. Brian has over 19 years of experience in the systems engineering and of aerospace, optical observatory, and defense systems. Prior to his role at Vitech, he served as the project manager of the United States Extremely Large Telescope Program, and has also held senior systems engineering management and senior leadership roles at Worldview Enterprises and the Large Synoptic Survey Telescope. He also worked at SpaceX in their early days, where he was responsible for specifying, designing, and testing of the Falcon 1 ground support systems. Brian has diverse experience with a number of MBSE tools and modeling methodologies. He holds a master's in systems architecting and engineering from the University of Southern California and a bachelor's in aerospace engineering from Cal Poly San Luis Obispo. Welcome, Charlie and Brian. Thank you for being here today. I'm going to do a quick run through of the agenda, hit our first poll question, and then I'll turn it over to them. Our agenda for today is a history and evolution of model-based systems engineering and digital engineering, advantages of Vitech's model-based systems engineering solution, precision digital engineering defined, BigLever feature-based product line engineering factory, and then the GENESYS Gears bridge that's going to enable precision digital engineering. So with that, we want to find out a little bit about you. So I'm going to go ahead and launch the first poll question here. It's, what is your role? There we have it. Systems engineers, we got 38%, design engineers 11, program managers 3, architects 16, and other 32. Very good. Thank you for your input there. Now, with that, I'll turn it over to Brian Selvey and begin our webinar here.
Thank you, Steve. So I'm going to start out going through a brief history and the evolution of model-based systems engineering and digital engineering. And the reason why this is, I think, very relevant to the topic at hand today is that where we've been and where we are now really sort of sets the tone for where there's still big, hairy, wicked problems that need to be addressed in the digital engineering and MBSE space. And our definition of precision digital engineering and our solution is really predicated on understanding where those gaps lie. So we'll start there and then move into our PDE solution. So MBSE today, it's still really in a state of flux. Systems engineering in general is still a very nascent discipline when compared to a lot of the other engineering disciplines. And if we just look at this on a notional timeline, without going into a lot of detail, the industry and the languages upon which it's all based have continued to evolve over time. We can trace our history at Vitech back to RDD 100, which stands for Requirements-Driven Design, a tool that was developed in the 80s. Vitech has 30 years of experience now at this point, really evolving out of RDD 100 into something that we've coined as the systems definition language, which allows our users to model in all of the standard systems engineering pillars, requirements, functional architecture and behavior, physical architecture, verification and validation, but also in terms of things like program management capabilities, especially engineering, all in a consistent, semantically precise way. Other things that have happened over the years is there's UML, the Unified Modeling Language, which came out of the software world, and then SysML, the Systems Modeling Language, came out of UML as a profile of UML that is a specialization for systems engineers, and that has continued to evolve since the mid-2000s, and now there's an effort to evolve it even further from V1 to V2. Vitech is a proud member of the team that is working on the V2 specification and reference implementation at this moment. And you'll start to see that rolled out over the next few years in tools. The dotted box that you see at the top represents Vitech's future. And we've got a really, I think, exciting roadmap of features and capabilities that we've specified and we'll be rolling out over the next couple of years. I'm very excited to have the opportunity to speak with all of you in the future and future webinars about a lot of those capabilities as they come to market. But why would anybody even go down this path? Why even undertake the effort of going the MBSE way? You know, because there is a time and a cost and a, you know, there are implications that you know affect all this. So there's always been the idea that the benefit is that you have one idea in one place. You know, you don't have to then go manually search through documents and find where every idea was ever spoken about, and then have to do you know, manual impact analysis to update those. Updates are rolled out automatically to you know, all affected instances. That in turn will reduce design errors and lead to faster design times. That's the promised benefit. Also, it is supposed to help with effective communication. Having consistent data, consistent information in a single repository, in theory, should help with communication, right? But that's not always the perception or the reality for a lot of users today. The tools are perceived, and I'm not just talking about Vitech, this is industry at large. The tools are, you know, often perceived as hard to learn. They're very complex in terms of the rich features and capabilities that they have. The user interfaces are quite can be overwhelming to look at sometimes when you first see them. The modeling languages require specialized training. You know, you can use the analogy of software engineering. You know, you can't just jump in and start coding on day one. There's an investment. If you want to, you know, code a web application, you're going to have to learn, you know, potentially Java and JavaScript. Same thing with MBSE. You're going to have to learn the semantics of something like the systems definition language and/or SysML. It's very hard to get legacy data into the tools in certain instances, especially when they're, you know, things that are in, you know, scan copies of old documents that are in PDF format, things like that. You need quite sophisticated artificial intelligence, machine learning to get that stuff in, unless you pull it in manually, which is time consuming. Often that represents a lot of a company's corporate knowledge base, and that information is something that you want to be able to use in future products. So it's important to be able to get in there. Some of the languages and tools are not completely semantically precise. And by what I mean by that is the ideas are not well completely defined so that it means the same thing to everyone. And in those instances, it's going to lead to imprecise communication from the beginning, right? Because there's already the opportunity for people to interpret the information in their own way. If it's hard enough for even systems engineers to understand it at some point, it's going to be even harder to communicate that esoteric data with non-systems engineers, disparate stakeholders. You know, if they don't understand those languages, it's going to be very hard to communicate that information to them effectively without somebody there to help translate. Still something we're working on, obviously, but still hard to digitally sync and transfer information from one tool to another in a seamless, consistent, coherent way. And then up until recently, especially with the help of BigLever and the work they've done with standards industry, ISO and the object management group, up until then, it's been very hard to manage variance in terms of things that vary and differ, as well as the common features of things in a product line. So that's where we are. You know, that's the promises and the perceived benefits and some of the issues that we've run into still up till today. Let's take a quick look at the evolution of capabilities throughout the years, because this will really set up what we mean by precision digital engineering going forward. So back in the way back times, when MBSE tools first started out, a lot of what happened was there was a reliance on a very expert systems engineer who pulled in source information from source documents, often having to reconstitute it, put it in manually into an MBSE tool, and interview a number of subject matter experts. The value that they then provided was the ability to weave that information using the capabilities of an MBSE tool into a consistent, coherent model. And they were able to then provide a lot of value back to the project to not only use their systems engineering skills and expertise to define an architecture, refine requirements, etc., but also to use the valuable capabilities of MBSE tool to look for gaps, inconsistencies between information in different pillars, that sort of thing. The consumers of the information back in the way back days were, especially, and this is still the case in a lot of industries and sectors, are very used to seeing information in document format. And so what would often happen is those MBSE tools would then generate documents from the model so that they've had the same look and feel of the input documents. It did aid in communication and aid in proper understanding of the information by the information consumer, but the artifacts back out, looked like artifacts in. We evolved from there, and we got better about being able to not have to rely only on the systems engineer to translate and manually input source document information, but auto ingest. And those capabilities continue to increase, but you can think about things like data that's in an Excel table format, for example, or things that have regular patterns like requirements that can be keyed off of with keywords like shall, should, and will. The tools were able to start to create pattern recognition and schema imports to be able to pull that information in automatically. We then got to the point where we realized often you need more than one model, right? You have multiple projects running. So you might have multiple projects within your MBSE tool. You may choose to model some of your business processes that impact or constrain or enable your product evolution. And those may be modeled in a separate project. The tools then had to have capabilities to create cross-project relationships and be able to share entity relationship and attribute information between those models, but still within the same tool. We then got to the point where we realized, oh, hey, it would be great to not only just document artifacts back out that look like the input ones, but to connect this very rich repository of information to other digital engineering tools in a more seamless manner. If one thinks about it, in terms of an example of a mechanical CAD tool, if there's physical constraint requirements, boundary conditions, interface requirements, and interface definition captured in the MBSE tool, as well as things like constraints like mass allocations, etc., it'd be really great to be able to seamlessly pass that information to your mechanical CAD tool. And then as the mechanical CAD design evolves, capture and pull back into the MBSE tool things like as designed parameters, like the as analyzed mass, those sorts of things, and then do verification compliance checks back in the tool. That's just one example, but there's numerous ones. And so the industry had to evolve in terms of creating these point-to-point connections through a number of interchange formats, either APIs or things like OSLC, etc. But typically, in the early days, these were point-to-point connections, really understanding the schema and ontology of both tools and understanding the use cases of what subset of the data that has to get transferred, and then building the connector that transfers that subset of the information. There's then a realization that, oh yeah, it would be really great to involve stakeholders earlier in the process so that they don't just get an artifact, a document at the end of the day, but they get to be involved in the process earlier and review and comment on content and help be part of the process of defining the system architecture early. And so the tools evolve to create viewer and commenter interfaces, and have evolved to web interfaces that can expose all or part of a model for a particular stakeholder to let them look at the information earlier. And then they obviously don't have to go in and learn the heavy client of the tool and interface with it that way. It's a much more streamlined way of interacting with the tool. And then we got to the point where we realized, oh yeah, that's a heck of a lot of point-to-point connections between the MBSE tool and others. Boy, it would make a lot more sense to create a digital thread bus with something like a publish and subscribe protocol, and the knowledge in that bus for understanding how concepts between typical types of tools have to be translated. And so then we got to a many-to-many sort of mapping capability using this as the transfer mechanism. There's a number of companies really working on this today in significant detail and making a lot of progress. And Vitech has been working with a number of them, and you'll get to see more webinars about the capabilities that we're rolling out in this area in the very near future. In fact, there's one coming up in November. And then we got to the point where we realized, oh yeah, not only do we have all these individual models within an MBSE tool, and they may have some relationships, there's a lot of sharing of components, desire to reuse information from one product to another and keep it consistent. Cloning or copying the information is not a desirable way to do this, obviously, because as the projects get larger and bigger and more complex, that information now violates the one idea in one place principle, and the information could then start to get out of sync in your MBSE tool, which is exactly the problem we had back in the old paper-based days. So rather than doing that, we need better product line engineering tools that have better methods for keeping consistent data consistent. So that's kind of the point that we are at today, in my opinion, in a very quick schematical way of representing it. But that's sort of the setting us up for where we need to go in terms of defining what precision digital engineering is now.
So now we're to our second poll question, which Steve, I'll hand it back to you for.
All right, thanks, Brian. So, what is your biggest MBSE challenge that you're dealing with? Learning a tool, modeling method implementation, extracting useful data, products, information from the tool, digital engineering environment integration and interoperability, or I am not using an MBSE right now. So it appears like the biggest challenge for most of the attendees here is typically what we see, right? Digital engineering environment and the integration and interoperability of things. So any thoughts on that, either Brian or Charlie?
Yeah, it's one of the hard problems that the industry is trying to address right now, and I think a few of the slides coming up sort of talk to that a bit more. But it's not surprising. That's the way the industry is moving, and for some of the reasons we'll show in slides coming up, that is not an easy problem to solve. But yeah, it's not surprising from my perspective.
Yep, certainly not. All right.
Great. Thanks, Steve. So I want to talk a little bit more about this digital engineering ecosystem. So one, if we start to zoom out outside of just the realm of MBSE and look larger, what does that look like? And what does that mean in terms of this concept of precision digital engineering? We're now in an environment where it's not just a single tool, as we've already talked about. It is a number of tools. It's a federated set of tools with data that needs to be shared. And there are these digital thread interfaces that are now being used as the interchange mechanisms to share data. And there are particular pieces of information that need to move from one tool to another, and they need to get translated and transformed from potentially certain types of data types to others to make sense in the other tools. And all these blue boxes that represent tools are typically made by different vendors, obviously. And where do problems typically arise? It's typically at the interfaces. That's, a system's heuristic of problems typically arise at the interface. And that's because there's a separation of ownership typically on either side of the interface. There's typically one organization responsible for building something on one side and somebody else on the other. And that can typically lead to communication issues or, just mismatches. So typically things break down at the interfaces. It's no different now when we look at a digital engineering ecosystem, which we can think about in systems terminology as a system of systems. And I really want to now hone in on these interfaces and talk about them in a little bit more detail. There's really two subgroups of these. One is the machine to machine, which I've already talked a little bit about in terms of we're getting to the point where there's these digital thread brokers. There's a number of companies working on this right now, but it requires a lot of understanding of the overall data structure in each of these and the types of transformations that need to be made. This can be done in a number of ways through trying to create master ontologies, which just means a way of trying to create a master language of all things in your universe, so that things get translated to that master ontology and then relocalized to the language of the other tool. There are several other approaches, but there's a lot of work being done here. But the old way of what I'm showing here on the left, the point-to-point, that still exists. It's just the wicked problem is that this is not scalable at enterprise scale, and it's not sustainable because these become fragile links. If a change is made on either side of the interface, it can make the link break, right? So there's a lot of research being done on digital thread brokers. The other wicked problem in my mind that I don't think gets very much press and attention is the machine to human interface. We don't really talk about that, but in the real world, decisions get made by people, right? And people are enabled to make better decisions through better data and information. And they can only make those better decisions if they understand the information properly that's being communicated to them. And the problem that we often have is that, I'm going to use the case of an MBSE tool, obviously that's what Vitech does, is we have systems engineers developing a model and then providing subsets of the information back out to a different stakeholder to help them drive their design. So if this is, again, the example of a mechanical engineer, the idea would be that a subset of the information for their specific component or subsystem gets presented to them. And if we only do the bare basics and just give them the subset, there can still be misinterpretation of what the information means, especially because they typically are not going to, we can't expect them to invest the time to learn specialized language, notation, and iconology that is foreign to them in their practice day to day. The wicked problem that we have to solve is how to not only give them the proper subset, but also translate it into the language, the terminology, and the iconology that they understand so that they can get the proper understanding. And only then can these two individuals, or more than these individuals, talk about that information in a way that they both have the same and proper understanding to make good decisions going forward. That's a wicked problem because the translation is not trivial, and every discipline has not only every discipline, but every discipline within an industry, and sometimes all the way down to the company or project, has localized language concepts that those individuals are used to. So the translation part is hard and often ignored. But without addressing it can lead to a lot of problems with improper communication. So before moving on to our topic on product line engineering capabilities, I want to talk about a little bit about the advantages of the Vitech solution. So there are a few things that, based on what we've talked about today, that the way that Vitech has architected their model-based systems engineering platform really tries to address a few of these major problems and issues that we've seen in industry up to today. The first is that we're starting with a precise natural language semantics. And what you're seeing on the right is a subset of our systems definition language. It's not all of the concepts, but it's a subset. And the idea here is that you can read through the entities and relationships and get a good sense of what's going on. There's no specialized iconology in terms of having to understand what specialized icons for relationships mean or specialized boxes mean. You can just read through these. So a component performs a function. And most people can understand what that means. Yeah, there's something physical that performs some behavior. Okay, that's pretty intuitive, and that goes for everything. That helps overcome that barrier of having to learn a lot of jargon because it's natural language. Another advantage is that our diagrams always stay in sync with the model content. The diagrams essentially come for free. They're auto-generated by your underlying data model. That's not always the case in all applications and all tools, but in Vitech tools, the diagrams get updated consistently all the time, and so that you don't ever have to worry about the view of the information you're looking at being inconsistent or out of date with the actual underlying data. We have standardized modeling pillars, which you can see over here on the left. That's integrated into our typical modeling methodology that we call strata. And it allows you to have sort of a roadmap of how to go in and start a model with requirements, functional architecture and behavior, structural architecture, V&V being your typical foreign systems engineering. But we've also added program management and specialty engineering. And those all are based on that foundational systems definition language. And the other thing that I'm very proud to say is that Zuken and Zuken Vitech are really embracing and champions of an open, connected digital engineering ecosystem. We have open APIs that allow you to connect to the digital thread and all best-in-breed third-party tools. Doesn't matter what the vendor is, if they're competing vendors. We really want to make sure that we enable our customers and our clients to pick the tools that they feel most comfortable with and meet their needs the best, and connect them in an integrated way. We've got additional capabilities coming online with views and viewpoints that we'll be able to talk about in future webinars, as well as analysis. The other advantage is that we don't think about only the system under design, which is typically what's done in most modeling tools. And in my example, I'm going to go through here is that of an aircraft. And this is what you would typically think of: your requirements, your functions, your physical structure of defining that of your aircraft. But there are other important things that impact that design, and Vitech's systems definition language and Genesis allow you to capture all that information, as well as the interrelationships. One of the key ones is the context system, which others may call the environment, the external environment. And for my example here, this would be things like air traffic control, the whole air traffic control system around the world, your airports, ground stations, the weather, all those things impact your aircraft, right? And we can model all those externals and their relationships to the system, model their constraints and enablers with the system. The other part that's important is the designing system. Apologize for the G wrapping around there. But the designing system, that is your enterprise. That's the company in which you work. And really what's happening there that's so important is that the way you're organized impacts the system under design. How your subsystem teams are structured will impact how you break up your physical architecture into subsystems so that there is alignment. Being able to capture that information in terms of work breakdown structure and work packages is important, because it often has to align with how you decompose your system. The other thing that once we now add BigLever to the equation is that it's not just typically one aircraft in my example here. Most companies that make aircraft create have a product line, a number of them, and there are variations between them. There are also commonalities. You can think about in terms of a a line of aircraft. They may share a number of common avionics, potentially even engines, but they may all have unique wings. A solution like BigLever Gears with its product line engineering capabilities really cohesively tied into a strong semantically precise model-based systems engineering tool like Genesys provides this rich precision digital engineering capability that is really unprecedented. All right, so before I hand this off to Charlie, let's go through and talk about what precision digital engineering means. Let's give it a definition. So the first is semantic precision. It means every element, relationship, and attribute in your model is explicitly defined and clear, and it means the same thing to everyone who understands the language. The second is views and data model synchronization. I already mentioned this. It's a thing that Genesys already does, but all views of your model are always in sync with the underlying data model. There's no possibility of looking at and consuming old or incorrect data when you're looking at a diagram. We need a formal approach to product line engineering. It doesn't require the retention of tribal knowledge or implementation of copy and clone techniques that are highly prone to errors and increased overhead. We also need unambiguous digital and human comprehension of the data. I've mentioned this a number of times in other slides, but not everyone and everything understands SysML or systems definition language. Not even all systems engineers understand them. The information consumer has to be able to understand what's being presented. That might require those translations that I talked about. Views and viewpoints or just simply presenting them a subset of the data is not sufficient. There needs to be a single master source for every idea. Now, because we're going to share information across tools, there will be a proliferation of the same concept being presented in different tools, and there needs to be a precise way of defining which instance of it is the master source and defining it concretely so that you can maintain configuration control, which is the next aspect of this, is that when information and data does need to get changed, there has to be a formal way of proposing, approving, processing, and federating those changes all across the digital engineering ecosystem. And the last one is really important because if you connect tools together and you simply just share all the data with everybody, with every tool, that's a increased amount of burden and overhead, and it's not really answering any question. It's just throwing data everywhere. And so the idea for a precise solution is it really has to be the right data at the right time for the right intent. Only provide the right information to the right consumers at the right time for each defined purpose. And so really the point here is you need to define why you want to share the data and then just share that data. So this webinar is really going to focus on these top three. These top three are really what we're focusing on now, but I wanted to give you a clear definition of everything that we believe is required for a precision digital engineering solution. So the last thing I'll go through is a quick example, and we'll set up the stage for Charlie and his talk, his second part of the talk on product line engineering. So before I came to Vitech, I worked for a company called Worldview Enterprises, and they made systems that looked like what you see over here on the left. They're high altitude stratospheric balloon systems that have a proprietary way of controlling them using atmospheric winds. And they have at least three different products. They have a space tourism vehicle, which you can see at the bottom, which is, the concept there is to take paying passengers to the edge of space where you can see the curvature of the Earth. There is this thing on the left called a stratolite, which stands for a stratospheric satellite. The idea is to get a lot of the benefits of a low Earth orbit satellite with remote imaging capabilities, but at a fraction of the cost because you can land, refurbish, and relaunch the asset, which really brings the price down. And there's a third one that's a variant on that called a Z-Class. I was brought in at the time right after they had validated the proof of concept that the idea worked. They had launched a number of these vehicles and showed that the concept is viable, but they were really struggling with enhancing the reliability, robustness, reusability of the system. And at that time, they didn't have any formal systems engineering, so they asked me to come in and stand up a systems engineering organization from scratch, which was really a lot of fun. but it required me to go in and define processes, tools, hire a team, and deploy them to addressing some of the issues that they were having with their products, and then really enhance them and build them up to scale, to productize them for delivery to a commercial audience. And so one of the first things I did was I said, all right, well, we need to start actually capturing all the systems engineering information in a model-based systems engineering tool. But I want to do it in a smart way. I know this is how I visualize the problem. I know I have at least 3 products. Each of them are going to go through upgrade processes and evolve over time. And each of our customers will request certain specializations of any one of those products. And that could be something like a specific payload. For the Stratolite, it could be a particular type of sensor, an optical sensor, a radar, etc. It may also be things like customizations to the landing system based on the operational environment. So those 3 things would constitute the product, the build, and the customer specializations would define a unique builder instance. But I also knew and wanted to make sure we accounted for up front that there is sharing of components and subsystems across these products. And I did not want to, clone or copy these things from one project to another and then allow them to drift and get out of sync over time. So I presented this problem to our tool vendor at the time, and I said, hey, this is the problem we're facing. What do you suggest in terms of architecting our modeling environment, setting up our modeling environment in a way that I can get benefits from and make sure our models stay consistent? And they said, that's a great problem, but we really don't know how to deal with that right now. So I ended up doing some things with packages and reusable libraries that kind of worked as a workaround, but it wasn't an ideal solution. And with that, I'm going to hand it over to Charlie, who will talk to you about Gears, which is a product line engineering tool that has a solution to this problem. So Charlie?
All right, thanks, Brian. So what we want to talk about next, as Brian mentions, next slide, please, has to do with how to deal with multiplicity across the product family. So systems engineering, the tools, the practices that are taught typically focus on how to do a really good job of, systems engineering, digital engineering for an individual product, throughout the full life cycle, get the full digital thread, digital twins, everything fully interconnected in a very precise way. But what we're faced with, and Brian's example, his anecdote that he just described is very typical. Nobody builds just one. So what we have to deal with is the fact that we're producing families of very similar systems, mostly common, but variations and features and functions. And so when we don't have good digital engineering practices and methods and tools and techniques to deal with that, leaves gaps in your digital engineering story. And those gaps are filled by tribal knowledge, right? You're not quite sure how this product is different from that one. Maybe you can see they're different, but you're not sure what's driving that difference. Typically you have to run up and down the hallway, find the subject matter expert and do some, extraction of tribal knowledge from somebody's head in order to deal with the multiplicity and the multiple products in a product line. So our premise and what we've been working on at INCOSE is the idea that the system family is really the system of interest that we should be engineering. It's not just the individual systems. And so how do we elevate from systems engineering into system family engineering? Next slide, please. So we've been pursuing this particular engineering problem and challenge and solutions for the last couple of decades here at BigLever. It's really nice that last year we finally were able to complete an ISO standard that brought together 30 different organizations plus others in the standards community. So INCOSE and ISO really brought a lot of power to bear. BigLever helped with the lead editing and authoring of this particular standard, myself and Paul Clements. And so what the standard does, it really defines what is truly needed to do a very formal, precision, thorough approach to product line engineering. And so when you have a family of similar products, systems that have variations in their features and functions, what we're going to do is apply a formally managed catalog of the feature variation, the distinguishing characteristics. We're going to consolidate our assets, like our models, our requirements, our source code, our mechanical design, our documents, our test cases, get those consolidated so we don't have multiple copies, but we'll have what are called shared engineering assets that are all shared across the multiple products without creating copies. And then we're going to apply automation in order to do the things that engineers have traditionally done through very manual tribal knowledge sort of techniques with multiple copies of their artifacts in a digital family. So at the end of the day, it's all about how can we take advantage of what's common, how can we get really good and formal and very digital in managing the variation. Next slide, please. All right, so how is this different from what we've been doing before? Organizations that have been building product lines for decades, if not centuries. They've been doing something, and that something is represented in the center of this particular slide. So you'll recognize some of these techniques if you're a practicing systems engineer or mechanical engineer, design engineer, software engineer. What are the techniques that we typically use? Clone and own is classic, right? I need to create a new product variant. I'm going to take everything I've done before on a similar system, and I'm going to make copies of everything. And I'm going to then start to modify it to tune it to, do exactly what my particular flavor of this product in the product line needs to be. And so that's great. You get 100% reuse on day one when you make your copy, but then you end up with a cloned copy. And now you've got two different groups modifying two copies, and you get 0% reuse after that. And in order to coordinate among them, typically that's where the tribal knowledge comes into play. Another one in the upper right-hand box there, the variation management silo. You see more and more tools now all saying, oh, we do product line engineering, we have variation management techniques in our tool. But as Brian says, we've got to get our tools interconnected. If we have each tool, each set of engineers using that tool, inventing their own notions of what are the variations, the distinguishing characteristics, everybody has to now create a model. There's multiple, probably different, incompatible, inconsistent representations of that. So the others, the reuse repositories, again, those are copy-based, branching and merging, trying to deal with your product configurations on configuration management branches. It's got the same issue of multiple copies on multiple branches. You can compare and diff and merge, but you never know why these two things may have diverged in the first place. So what ultimately characterizes all of these approaches is the tribal knowledge required to deal with it. Very non-digital engineering techniques when you're dealing with the product line problem. Even if you have very formal digital engineering techniques for everything else in the life cycle, if you don't solve this problem, you really haven't solved digital engineering, and certainly not precision digital engineering. The quote off to the left just shows a study that was done and actually characterized this product variation and product line problem as the leading source of complexity in engineering organizations. So it's not just a problem, it's the biggest problem that you're probably confronting in running an engineering organization. And so that means we need to really pay attention to it. So what we're going to do is move to the right-hand side of this diagram, move into what we call feature-based product line engineering, and do a very formal model-based capture of all that tribal knowledge that used to run around up and down the hallways, and we're going to put it into models and systems to help us deal with that. Next slide, please. Okay, so this is an example, just to emphasize the complexity of this early generation. We're showing a clone and own or a branch and merge version here. But imagine you've got a product family with all the products, around the circle there, and product B maybe was created starting from a copy of product A. We put a team on product B now, create the new variants that will support new distinguishing characteristics on that particular product. Well, imagine now we find a safety critical defect in product B. Wow, question is, did I get a copy of that from product A? What was the source of this critical defect? Maybe product E and product D both got copies of that from me. So now, not only do I have a safety critical defect, but anybody that borrowed, my assets to create their clone, they've got the same thing. And so now, without, any formalism other than just, yeah, we made a copy, you're going to have to rely on your subject matter experts and the tribal knowledge to track this down, the legacy of that particular defect and the resolution of it across the product family. So that's what all these interconnected lines in between are. It's those informal meetings, emails, documents, tribal knowledge, conversations in the hallway that are required to manage your product line. And those are rife with errors and mistakes and risks. And I fix a defect in a couple of places and I miss one, and now I have to find it and fix it again in another member of my product line. This is that complexity that Michelle talked about. And if you've lived this problem, I don't need to emphasize it anymore. Next slide, please. All right, so the economic cost here, we're going to represent this in a graph like this. What we're showing is over a period of time, enhancements and defect fixes for a team managing product line. There will be a distribution of effort on what was the effort required to address an issue that impacted 3 products. What's the amount of effort required to impact issues that impacted 6 products? So you can see, of course, anytime you make a change that impacts more products, it requires more effort in order to do it. And this is kind of just the normal expected cost curve over time of our engineering organization as we're managing a product family. So we're going to show how to do a much better job of this. Next slide, please. All right, so here's just a build showing the ISO standard and the way we implement it here at BigLever. So imagine off to the right-hand side now, there's my product family for my product line. But what you'll notice is our engineers are not working over there on those individual copies of all the assets anymore. They're working over to the left. And this is the key set of elements, the 4 elements in the center here of the ISO standard. In the upper left, the feature catalog. This is a formal digital model with very precise semantics that describes distinguishing characteristics among the products in our product family. And so you might recognize these as, when you say buy a new car, you get to pick and choose among options and variants that you want on your vehicle. And those are abstract, distinguishing characteristics that are independent of, you're not looking at requirements or code or picking what parts you want on your car. You're picking and selecting among distinguishing characteristics. So that's the role of the feature catalog. Now, if we look down in the lower left, those variations, distinguishing characteristics, will impact everything across the systems engineering lifecycle. Our code, our requirements, our design models, our test cases. And so what we can do is say, if I have an optional capability, say I've got pedestrian detection on my car, well, that choice of whether we include that or not is going to impact everything across the life cycle. And so one distinguishing characteristic, you can see it reaching down into our assets and able to, control the variation that needs to exist in our models, in our requirements, in our mechanical, electrical, software design, test cases, documents, and so forth. So when we do this now to describe a product, in the top center, this notion of bill of features, we pick from our we select from our feature catalog for this particular product, what are the options and variants that I want. We've got that model now that we can feed into a configurator. It will pull our shared asset supersets in the lower left, that superset V. It will pull it through the configurator, and it will sort out through the variation points in our assets, what is needed, what is not needed based on the selection of the options and variants. And it will produce product A or product B or product C, based on the input spec there. So now if I fix a defect, if I find a defect in product B on the right, I don't run up and down and try to fix all the generated products. What I do is go back to the factory and say, you generated a defective product for me, please fix your factory. And your PLE factory now can then fix it, find the root cause of that problem, fix it, push the button again on my configurator and regenerate product B. But it can also regenerate any other product impacted, product D, product E, that might also be sharing that defect that came from a shared asset superset. So that's the key idea. You find it once on the right, you fix it once on the left, and now you can automate the propagation of that fix or enhancement across your entire product family. Right, let's go to our next slide, please. So this is the economic savings then. The blue cylinders across the bottom, no matter how many products are impacted by a defect, as I mentioned, you find it once, you fix it once, automation will take care of propagating it across all the members of your product family. So the green portions of these cylinders represent the work you don't have to do anymore. And this is an enormous saving, typically, orders of 3, orders of 4. And so the question is, if my engineers are triple, quadruple productivity, that means they get a normal day's work done in the morning. What do you have your engineers do now in the afternoon with that extra capacity? And many good answers to that question, none of them having to do with repetitive work, branching, merging, diffing. It's all about adding new business value to your products and your product family. Next slide, please. Okay, so go ahead and proceed again. We're going to talk specifically now about the work that BigLever and Vitech are doing through what we call the Genesis Gears bridge. So if we sort out our problem in 3 dimensions, if you look at it from this perspective, multidiscipline going vertical here is the dimension where you're doing your digital engineering across the life cycle, getting that precision digital engineering for your requirements, your models, your test cases, and your code, fully interconnected digital representations. Going left to right is the multiple baseline. So this is the evolution of all of that over time. So imagine your supersets in your PLE factory, of course, they're evolving. So we have to deal with that. The key thing that we're adding through this bridge is the multi-product dimension. So I showed you that ISO standard. As we complete the picture here, if you can do a really good job in each of these 3 dimensions, providing the technical digital engineering underpinnings, then you end up with true precision digital engineering. So next slide, please. Here's just a real simple screenshot. What you can see are a couple of views, a browser view and a diagram view from Genesis. These are for blocks. The extra dimension of variability you can see are indicated with the little gear icons. This is where we're dealing with variability now. Let's just focus on the right-hand side of the diagram, we have two blocks, both indicated as variation points. That means they can either be present or not present in a particular configuration. So power locking on the left, this would be power door locks, for example, on a vehicle. If that is included, if we look in our feature catalog and say, oh, this product needs power locking, then this block will be present. But on the right-hand side, we can see a block that was omitted because that particular feature was not needed. And so there's little bits of logic down underneath each of those blocks that determines the in or out of a particular block. Next slide, please. We'll wrap it up here. These are just some examples of companies who have been practicing digital engineering through feature-based product line engineering for many years here at BigLever. You can just recognize the names as major initiatives in large companies on major product lines. You can go to our website and find those published case studies and videos to learn more. Next slide, please. And then finally, the industry in COSI, OMG, ISO, are contributing now to codifying, teaching, educating, spreading awareness on how to do feature-based product line engineering. The OMG standard that Brian mentioned, we worked with them to make sure they're going to be ISO 26580 compliant, so the variation points in SysMLv2 will follow the description of the standard and the approach that I just described here. So really nice industry consensus in building out these standards and engineering practices. Next slide, please. Okay, so I think we can wrap it up. Of course, any interest about seeing a demo, learning more, just reach out to your Vitech or your BigLever team. Go to the website and request more information, and we'll get humans talking to humans to help see if we can help.
All right, thank you, Charlie. Thank you, Brian.